All right, so let's get started with infinite limits. So when do we use these types of limits? So let's say we have a function, the typical y equals 1 over x. And we think, well, what would be the limit? Let's call this function f so we can not write the same. Let's write limit as x goes to 0 of f of x equals what? All right, so let's take a look as we approach 0. We're going to start approaching from the right in our x-coordinate. So we're going to be traveling on the graph in this direction. And you see as we start getting closer to our 0, we start going towards positive infinity. However, as we travel from the left, we're going to start traveling towards negative infinity. And then it begs the question, which one do we pick? Positive infinity, negative infinity? And we tend not to discriminate, so we say that this limit does not exist. So let's just erase the equal sign and say that the limit does not exist. However, we can say that the limit as x approaches 0 from the right in this case is positive infinity. I'm going to write positive even though you don't need it, but it's positive infinity just to emphasize it. And the limit, let's see if I can fit it here. Seems like I can. As x goes to 0 from the left, so in that case would be going to negative infinity. And those limits come from, if you will, this comes from my red arrows, and this one comes from my orange arrows there. All right, so that is going to be one case when we have that the one-sided limits do exist and they're infinite, but the limit itself does not exist. Now let's contrast that with this next graph. And so we're going to say, for example, 1 over x squared. So in my graph. And we're going to take a look at what happens with the limits. As we approach from the right, my graph will be traveling towards infinity. And as I approach 0 from the left, I am also going towards infinity. So in this case, we have that the limit as x goes to 0 from the right of 1 over x squared, let me write the function because I didn't give it a name, is going to be positive infinity. Now I'm just going to write it as infinity. And the limit as x goes to 0 from the left is also going to be positive infinity. So when the two one-sided limits coincide, you say that the limit itself is equal to that, in this case not a number, but to that which would be infinity. So those would be our two different cases when we're talking about infinite limits. Whenever we have that the one-sided limits exist, but they do not coincide, and they're infinite, of course. And the case when the one-sided limits are going to be infinity, but they will coincide. They could also go to negative infinity as well, but in that case, we do say that the limit exists and is, well, it's an infinite limit, let's say, Usually we tend to say limit exists only when they're finite, but in this particular case we are considering infinite limits. So let's go ahead and do a few examples and determine our one-sided limits and then our limit themselves for each for rational functions. So let's go ahead and do that. The limit as x goes to, let's say, 3, and then we're going to have here x plus 1 over x squared minus 9. So something that will have a 0 in the denominator, so we have an infinite limit. So in this particular case, notice that if I evaluate here, as we used to do for computing limits analytically, you get 3 plus 1, so the numerator becomes 4. And then if you evaluate here, you get 9, so 3 squared is 9, minus 9, so that becomes 0. So you have something of the form 3 divided by 0. So I don't have 0 over 0, so I don't want to factor. I have 3 over 0. That's going to be an infinite limit. That's a good note to write here. So you remember that. When evaluating, I couldn't fit it. If you get 0 over 0, as you know, you want to factor. If you get any number that is not 0 over 0, then you have to think about an infinite limit. So you're talking about an infinite limit there, so that whenever you evaluate, you remember that. So if you have 0 over 0, you have to remember that you need to factor. In this particular case, I have 4 over 0, the form of 4 over 0, so I'm going to look at an infinite limit. So what I'm going to do is I'm going to try to figure out the sign. So how do you figure out the sign? Well, remember what we do before when we looked at zeros. And I'm going to factor just so you see it, even though you don't need to factor. I said you don't need to, but I'll factor it just so you see what's happening. And of course, I'm not going to fit that. What a mess. But I just want you to see what's happening here. So you see this term, x plus 3, is making or giving you the 0 in the denominator. So what we want to really find out is to the left of that number and then to the right of that number, does the sign change as you cross through 3? So graphically, if you have 3 here, will the sign change, say, from positive to negative, or will it go from negative to positive? Will it stay from positive to positive? That's going to determine to what infinity is going to be going. So let's go ahead and grab a number very close to 3. But that is not past negative 3 or negative 1 that make this number 0. So if we mark the numbers that make all the zeros here, we have positive 3, which is our point of interest. Then we have a negative 1 from this one. And then we have a negative 3. Those are the possible points where the function will change signs. Everywhere else, if you're negative here, you're negative here. If you're positive here, you're positive here. As long as you don't cross through either negative 3, negative 1, or positive 3, your sign is not going to change. Because in order to change signs, you're either going to have to have a vertical asymptote or go through a 0. So I'm going to pick a number that is easy to evaluate. So for example, I'm going to pick 2 here, and I'm going to pick 4 here. And I'm going to evaluate my function at those points. So at x equals to 2, I'm going to evaluate my function. I get 2 plus 1 divided by 2 squared minus 9. So I'm going to get 3 over 4 minus 9. I really don't care what the number will be. I just care about that this number will be negative. So positive times negative, this number is negative. So I know that here, I'm going to have that in this whole interval, the function will be negative. Now I look at what happens at x equals to 4. I'm going to evaluate my function there. So I'm going to have 4 plus 1 divided by, my bad, 4 squared minus 9. So 4 squared is 16 minus 9. That is a positive number. And then 4 plus 1 is positive as well. So this whole thing is positive. If you really don't feel comfortable doing that, you can just put it in your calculator, look at what numbers you get, write them down, and you determine whether it's positive or negative. But I think they're easy numbers, so you really don't have to. In particular, if you pick numbers that are easy to evaluate. Sometimes you'll have to deal with fractions, but such is life. All right, so I get that that is positive there. So what this all gives me then is that the limit as x goes to 3 from the left, so this side, of this function that we're going to call f of x, if you will, so we don't have to write the whole function all over again, is going to be equal to negative, I got the sign from this one, and I know it's going to go to infinity because I have something of the form a over 0 where a is not equal to 0, so it's going to be negative infinity. So I know that since I have a 0 in the denominator and not a 0 in the numerator, I'm automatically going to one of the two infinities. I just got to determine the sign. So now from the right, I get that on the right side of 3, the function is positive. Therefore, the limit as x goes to 3 from the positive side is going to be equal to positive infinity. And since these two guys do not match, then the limit itself does not exist. All right, so that's what we have there. So you have an example of one where the limit does not exist. So let me write one where the limit will exist. All right, so let's write one like the following. Limit as x goes to 2 of, say, x plus 1 over x squared minus 4x plus 4. So you know that's a perfect square, and that's kind of what we need in order for the limit to exist. More or less what, like the example I gave you before. So let's take a look at what happens when we evaluate directly here. I get a 2 plus 1, 3, over 2 squared is going to be 4 minus 4 times 2, 8, so negative 4 plus 4, 0. So when you have something of the form a over 0, it's going to be an infinite limit. So all we need to do then is determine the sign. So I'm going to grab my number line, grab 2, and look at where's another point where this becomes 0. The only zeros of the denominator, the only 0 is x equals to 2, so I just picked that one. And now I'm going to put negative 1, which is my other 0, just to make sure that the numbers I pick to evaluate the function are not to the left of that. So we're just to the left of 2, but still to the right of negative 1. And so you could pick 1, but I am going to pick 0 because that's even easier to evaluate. And then here I would definitely pick 3 because it's a little bit easy to evaluate. So at x equals to 0, we get that evaluating at 0 is 0 plus 1 over 0 minus 0 plus 4. So 0 plus 4, which is 1/4. I don't care about the number really, but I already wrote equal. All I care about is that it is positive. So right here I have that my limit from the left is going to be positive infinity. Let's see what happens from the right. So from the right, I have that at x equals to 3. When you evaluate here, it's going to be 3 plus 1, so 4, over 3 squared, 9, minus 4 times 3, which is 12. So 9 minus 12 is going to be negative 3, plus 4 is going to be positive 1. And as I said, I care about only the sign. That's all I care about in this case. So we have that is going from the left, going to positive infinity, from the right, positive infinity. Limit itself will be positive infinity. So let's summarize it all in one single line. Let's call this function g if you want. X goes to 2 from the left of g of x. I'm going to say it's equal to the limit as x goes to, not equal, 2 from the right. And this is going to be positive infinity. And from that, I know that the limit itself will be positive infinity. So that's how easy these are. So you just have to evaluate whenever you have some number over 0, then you're going to be having an infinite limit, and then you just have to determine the sign at that point. All right, let me do one more example, but that's going to be no longer a rational function. It's going to be another type of function. So let's go ahead and do that. Okay, so this example is a little bit different because we're going to have, for example, limit as x goes to 1 from the right, and let's say something like x natural log of x minus 1, for example. So a little bit different, isn't it? But you have to remember, so as x goes to 1, you have no problem with this one whatsoever. So you could split this. That one gives you a 1, no problem. But then you address this one here. And what happens with this one? You have to remember what is the graph of the natural log of x. And the graph of the natural log has an asymptote at x equals 0. And this right here is just the graph, or the graph of this function will be the graph of the natural log shifted 1 unit to the right. So let me go ahead and draw that one. So my asymptote gets moved 1 unit to the right. And this would be the graph of that function. So you see, this one is going to 1, but as you approach x from the right, 1 from the right, you start going down rather rapidly to negative infinity. So this one right here is more, you have to solve it more with the graph, and it's just going to be negative infinity. And just to close, there's another function like this that you know and you have used in the past. Let's do, for example, limit as x approaches pi over 2 from the right, let's do this time, of the tangent of x. So this one you don't have to do anything but look at the graph. So remember, what is the graph of the tangent? Well, you have two asymptotes, one at negative pi over 2, and then you have one asymptote at pi over 2. And then the graph is going to be going, with this one, like so, sort of. And then it's going to have an asymptote there, but I'm approaching pi over 2 from the right. So what's going to happen is I'm going to have to draw another period of the graph. I'll stop right there. And as you approach pi over 2 from the right, you're going to be going to negative infinity. If you were approaching it from the left, you would be going to positive infinity. So it does matter from what side you're approaching. So negative infinity. And now the limit as x goes to pi over 2, since they're different from the left and the right, it just doesn't exist. All right, guys, we're going to leave it at that for infinite limits, and I'll see you next time.